Okay, so this is the last problem on my algebra-based physics final, second semester. I said that already. I already did this problem, and I made a video. Boom, there it is. But I made a small error at the end, and I'm just going to redo it. If I would have made, I'll tell you about the error in a second. Okay, so here I have a star that can be seen by a star. Can be seen I wrote this question. Can be seen by the human eye if it has an intensity of, so I equals 10 to the negative 7th watts per meter squared. A supernova occurs 55 million light years away. So I'm just going to call that R equals 55 times 10 to the 6th light years. What is the minimum power of the supernova? Okay, so if I can detect it, then it's this intensity, at least. So intensity is the power divided by the area. That was one of the formulas I posted. So if I know the intensity, all I have to do is find the area. And what does that mean? So suppose here's my supernova event. And that light is going to spread uniformly over a sphere, because it's expanding in all directions, of radius r. And so what's the area of that sphere? Well, the area of the surface area of a sphere is 4 pi r squared. So if I want the power, I can say power is equal to the intensity, which I know, times the area, which is 4 pi r squared. But wait, here I have a problem. Intensity is in watts per meter squared, and this is in light years. So I need to convert. Now, how do I convert light years to meters? I did this the long way. On the test, I gave a couple of hints, but let's just do it the long way. So if I say the speed of light, c, is 3 times 10 to the 8th meters per second. And that's going to be the change in position over the change in time for light. So the question is, if it goes for 1 year, how far did it go? So delta x is, actually I should say 55 million years, right? Because that's what the answer is up here. So delta x is going to be c times delta t. But I need to get delta t in seconds. So delta t is equal to 1 year. Now I want to convert units, and the key to converting units is to multiply by a value that's equal to 1. So if I multiply this by 1, I don't change anything. So here, if I multiply this by 365 days over 1 year. So 365 days is 1 year. So this quantity right here is the value 1. So it doesn't change this idea. Actually, that's 1 year. I need to change that. This will give me the time. I'm finding the distance for 1 year, 1 light year. But the years cancel, and I get the answer in days. So now I'd have 365 days, but I need it in seconds. So let's do this. 24 hours in 1 day. Now the days cancel. Now I need to convert that to seconds. I can multiply by minutes and then seconds, but I know that there are 3,600 seconds in 1 hour, because it's 60 times 60. And so this gives me, now I can pull out my calculator. This will give me the time for 1 year in seconds. So I have 1. Why did I put in 1? I don't know. 365 times 24 times 3,600 times. And I get 3.15 times 10 to the, I think it's 7th seconds. Okay, so that's the time for 1 year in seconds. So now I can say delta x, I can say r is 55 times 10 to the 6th light years. And I know that 1 light year is, let's say I didn't do that. 1 light year up here is going to be 3 times 10 to the 8th meters per second times 3.15 times 10 to the 7th seconds. And the seconds cancel and I get meters. So I'm just going to put that in. So 1 light year is 3 times 10 to the 8th times 3.15 times 10 to the 7th meters per light year. And that's my R. So my R value is going to be, I need to put that in again. Now you got to be careful with your scientific notation here, but that's something that you should be careful with anyway. So 55 times 10 to the 6th, enter. 3 times 10 to the 8th times 3.15 times 10 to the 7th times. And I get 5.198 times 10. Oops, it's 23rd meters. So now I can go back up here and calculate the power. So power is going to be the intensity, 10 to the negative 7th, 4 pi, and then I'm going to get 5.198 times 10 to the 23rd, all of that squared. Now be careful with that, okay? I know people make a mistake. And be careful with this too. So 10 to the negative 7th is entered as 1e negative 7, right? Because this scientific notation says 1 times 10 to the negative 7th. It's not 10e negative 7. Okay, that's one error. Now I'm going to multiply by 4. Oops. Okay, 1 exponent 7, enter. I didn't enter it. And then I'm going to multiply by 4, multiply by pi, turn that into a number. And then I'm going to take this number, 5.198 times 10 to the 23rd, enter, and then I need to square that. Now I can multiply it together. And I get 3.4, I'm going to say 3.4 times 10 to the 41 watts, which is a lot of power. That's why it's called a supernova. Okay, so here is my work. This is a unit conversion problem. It really wasn't that hard. Here's my work before. The only thing I did this right. I did everything the same. But down here I said the power, and I used this. And this is the distance for, this is 1 light year. I didn't multiply that by 55 million light years. Okay, so then I did that, and I fixed it, and I got the same thing. But that, again, this value is the minimum power, okay, in order to be able to detect it. It could be more than that, and you'd see it brighter. The end.